Okay, good day. This is AP Calculus. I am Mr. McCully, and this is the presentation for section 7.2, Solids of Revolution. Let's get right to it. Today we are going to be talking about finding the volume of a solid of revolution using a disk method. And this is something that we can use to generalize some formulas from geometry that you may have. And if we have an opportunity, I will certainly um, uh, derive uh, the general cone function based on surface of revolutions in class. But we're going to do that. We're also going to find a solid of revolution using the washer method, and we're going to find the volume of a solid with known cross sections. That one's the challenging one. So what does it mean when we're talking about a revolution of disk method? Well, it's hard to draw a picture of it, so I kind of grabbed one off the internet. So basically, when we find the area under the curve, we're finding the area of an infinite number of small little rectangles. Now, if we revolve that rectangle about the x-axis, we then get what's basically going to look like a disk. So when you say I want to find a volume of revolution, if I have a defined function, I can use an integral along with the area or the volume of a cylinder function. And remember, just off to the side here, the volume of a cylinder is pi r squared, the area of the base, times the height. And so when we look at this, our radius is the distance from the x-axis to the point on the curve. That is our radius, and our height is this little distance here. So we can see it. There is our pi. There is our radius squared. Since we're adding up all of um, these little rectangular disks or rectangular revolution disks that we have, and then dx, that's the change in height. So we can real clearly see that this volume equation using the disk method is derived from that equation. All right. And then the second thing they asked us to talk about was the washer method. And the washer method is a little bit or a little more than the difference of the area of two functions, the area between two curves, revolved around the x-axis. Now, we did the area of two curves, so let's say I have two areas or two curves there, and I want to find the solid of revolution around them. Well, it's just the difference of those two curves, and then we subtract those volumes. So basically what this expression says is I find the volume of this inner curve, and I find that volume of revolution, and then I find the volume of this outer curve, that as a revolution, and then I subtract it, and they say that they're being made into disks. And then finally, um, volumes of solids with known cross sections. For cross sections of area A perpendicular to the x-axis, that volume is going to be from A to B times the area of whatever that cross section might be. And in the examples, I'm going to do a cross section that is both a square and a equilateral triangle, which is kind of cool. And you can also do it perpendicular to the y-axis, just like we can do find the area under a curve with respect to the y-axis as well. So we might as well just jump right into it and talk about it. So I am in the book again. I'm on page, let's see here, it's 465, and I'm looking at number 1. And basically what they want us to do is they want us to find the area, the surface of revolution of y equals the square root of, let's see here, it's 9, that's not a very good 9 minus x squared from 0 less than or equal to x less than or equal to 3. And so what that thing looks like is we know that that is the graph of a circle, and it is going to have a center at 0, 0, and it's going to have this value right here. So there's not 9. Come on, Macaulay, get with it. Here's 3 on the y-axis. Here is 3 on the x-axis. And we are trying to find this area right here. And then what we're going to do is we're going to revolve that around the x-axis. Now, what you kind of want to think about is, again, we knew that this is a circle equation, and so the volume, if I rotate a circle, I'm going to get a sphere, and since I'm only going from 0 to 3, I'm only going to get a half a sphere, and I'm just going to find that volume right there. So let's set it up the way that we had it in the directions. And so I go back up to this equation here, and my r is going to be the equation of the curve, that right there, that's going to be the r equation. I'm going to square that, find the integral of that, the definite integral of that function squared. I'm going to multiply by pi. And so we're going to set this up as it's going to be this volume that I'm looking for, v right there, once I've rotated it, is going to be pi, the integral from 0 to 3 of 9 minus x squared to the 1/2 power. That's what the square root does. But again, the function tells me to square that, so I need to do that. So we're going to put a square around that, and then dx. Now, the square and square root, those things are going to cancel. So I've got the integral, or I got pi times the integral from 0 to 3 of 9 minus x squared dx. Well, I can do the simple power rule on both of those two terms, and that will give me pi times the quantity, and this time I can do the quantity, of 9x minus 1/3 x to the third, and we're going to evaluate that from 0 to 3. Now, when I plug 0 into these two terms, I'm going to get nothing, so I can just say that it is pi times 9 times 3 minus 1/3, 3 to the third, and 9 times 3 is 27. 3 to the third is also 27, but when I take a third of that, I'm going to get 9. 27 minus 9 is 18, so this is 18 pi units cubed is what I'm going to go with for that. That's going to be our first solution. All right, so our next one, let's do one that's the kind of doing the disk method. And basically what this one wants us to do is it says, it gives us a couple of different curves, and there are a bunch of questions that go along with this particular problem, but it wants us to rotate the region R2 about the line y equals 1. Now we've been rotating, the first question asked us to rotate about just the x-axis, and that's what most of these equations do. So we're going to have to do a little bit of manipulation of the function before we can do that. So we are essentially trying to find the volume of, let's get in there nice and tight with a small one. I want to get this volume, not as, oh, that was weird. Maybe it'll do better if I go like this. Okay, they want us to take this function here and not rotate it about this, the x-axis, which most of the rotations do, but it wants us to rotate about the line y equals 1. And so what this thing's going to look like, again, we're rotating it around, And so I have a straight line, the line y equals x, that's this line right here. And then I have a parabolic curve, y equals x squared, right here. So if I were to rotate that, you think of a straight edge cone on the inside, and then on the outside, I'm going to have almost like a mirror shape on the outside. So I got to set that up. And again, we're going to use this equation right here, where it's going to be pi times the top function squared over the bottom function squared. But I've got to transform this this thing so that I'm rotating about the line y equals 1. Now that's kind of complex, and so the best way that I can think of explaining how to do this well is to actually write out the equation and what it looks like, and then kind of describe how you're going to go about doing it when you are actually asked to do these reflections or rotations about lines that are not the x or y axis. So the equation turns out to be, and I don't want that, we can leave it v, purple's good. The equation is going to be pi integral from, well, 0 to 1, because we're only going from 0 to 1, so that makes sense. And then it is going to be the quantity 1 minus r, sorry, I just need 1, I don't even need that. Let me rewrite it one more time, see if I can get it right. It's going to be 1 minus r squared, oops, I'll get it right, I promise. 1 minus x squared, that's this equation, squared, minus 1 minus x squared dx. Now, again, this is kind of a weird, how do I come up with this thing? Well, the way you think about it is this way. What kind of transformation does this function, this 1 minus x squared, have in relation to this y equals x squared function? Now, if I were just to do this line over this line and I rotate it around, I get a cone shape on the outside and a curve shape on the inside. And I don't want that. Okay, I want the straight side, the cone shape on the inside, and the curve on the outside. And so let's talk about it in terms of the transformation in regards to this 1 minus x squared versus this y equals x squared. Well, back in pre-calculus, we said that this negative made it a reflection about the x-axis. So it's going to reflect about the x-axis. And then this plus 1 will move it up 1. So I'll get something that kind of looks like this, kind of like this curve right here. And then this same thing here, this negative x is going to reflect it about the x-axis. So I have something that looks like this. And then this plus 1 pushes that up. So now I have a straight edge and a curved edge. And then when I rotate it, I'll get the same volume as if I rotated this one about the x-axis. That's how we're going to do these. All right, so let's get to doing it here. So let's do some simplification. I have to square both of these, and please remember you cannot distribute exponents across addition. So we have to multiply these all out. The first one becomes 1 minus 2x squared, and then plus x to the fourth. Let's write that better one more time. 1 minus 2x squared plus x to the fourth. Then it's minus 1 minus 2x plus x squared dx. And just for the sake of expediency here, I'm going to, and this is from 0 to 1, and I have 11 there. I don't know where I got that. I'm sure you guys are all screaming at the screen. Quit screwing up. Simplifying this, making it into collecting my like terms, I'm going to have x to the fourth. I have minus 3x squared, and then minus 2x. That's dx. And again, I'm just going to evaluate this in the context of simple power rule on each term. So I've got pi times the quantity. It'll be 1/5 x to the fourth, and then it'll be just x to the third because I have the 1/3 divided by 3. That'll cancel that out. And then it'll be minus just x squared. And again, I bring the 2 up. I add 1 to the 1 exponent. That gives me 2. Divide by 2, and the 2's cancel out. And this is going to be evaluated from 0 to 1 again. And so when I plug in 0 to all of those terms, I'm going to get nothing. So all I have to do is I have to plug in the pi, and then it'll be 1/5 times 1 to the fourth minus 1 to the third, and then minus, it'll be minus, why did I get, this should be, I made a mistake here. Minus a negative makes that plus a positive. And then when I do the integral of that, I get a plus there. So I'm going to get a plus here. and then it's going to be 1 squared, and that ends up being, after you calculate all of these, I've got a positive 1, I've got a negative 1, those cancel. 1 to the 4th is 1, times 5 is 5th, times pi is pi over 5. I did that fairly quickly. Let's hope I didn't screw it up too much. All right, now the hard one. Let's see how we're doing for time. Oh, 15 minutes already. Okay, the hard one, number 72. So number 72 says this: we are going to take this circular function here, this x squared plus y squared, and equal to 4. So this is the equation of a circle. And so on my x and my y-axis, it's going to go, this is going to be a 2, this will be a 2, this will be a negative 2, and this will be a negative 2. All right. And so what it wants me to do is it wants me to use this function as the base of a bunch of squares. All right. So it wants me to do it as a base of a bunch of squares. And so think of it this way. If I laid this flat on the side and I made, instead I made this y and this x, so I'm kind of shifting it a little bit. So I'm kind of going left to right. This way is up and down, sort of, I suppose. So this is negative down here, and here's positive up here. And so I'm running squares this way along the line. So I get a bunch of squares. So you're going to get this kind of weird shape, and they actually draw it in the book, so you might want to check. So when it's closer, when I'm on, like, say, this portion here, that square is going to be smaller. And then the closer I get to the edge, the smaller those squares are going to get. And I'll have this kind of odd shape that's gonna get wider as I go out, as it gets bigger, and then it's going to shrink again. And it's just a bunch of squares. So it's, like I said, if you check in the book, and it's they actually draw pictures of this on page 464. And this one was number 72. They actually draw pictures of the shapes, the solids, that I can't copy them. But again, basically what's happening is I'm creating a volume that is a bunch of squares based on this circle. So it's a bunch of squares stacked together based on this circle. And so we're using this equation right here. So again, we want to go back to this. So here's what I'm going to do. First thing I want to do is I'm going to solve this. I want to solve this function for y. And that's pretty easy. It's y equals plus or minus the square root of, let's see here, it'll be 4 minus x squared. Okay. All right. So I can't do plus or minus, okay, because the plus represents this part of the circle, the minus represents this part of the circle. So what I'm going to do is, I notice that this section here is symmetric to this section, so I'm going to make it y equals 2 times the plus 4 minus x squared. So I'm just going to take the volume that I calculate on the top and double it. That's going to give me the one on the bottom, and that gets rid of my plus and my minus. So that's pretty simple. All right, so this is my length right here, and I want it to be a square. So if this is the length that I want right here, then this length right here is the same as that. So the area of each of these squares, as I progress along the x-axis, and they get bigger and then they get smaller, is going to be the x squared function. So since the area of one square is essentially going to be y squared, my integral, so my total volume here, my a of x function in this case, is going to be 2 square root of 4 minus x squared squared, which turns out to be 4 times 4 minus x squared, or 16 minus 4x squared. So my volume from A to be of a of x dx, and again, that's the equation that I got from here, is going to be equal to the integral from -2 to +2, from here to here, of this area function, so 16 minus 4x squared dx. And this is a simple integral because it is, I got two terms, and I could do the simple power rule on each of those two terms. And then that's going to give me, let's see, it'll be bracket, it'll be 16x, and then it'll be minus 4/3 x to the third, evaluated from -2 to +2. All right, now, just for time's sake, I'm going to plug in, and I'm going to, and it's real quickly, it ends up being 32 minus 32 over 3, and then minus -32 plus 32 over 3. And then that gives you 128 over 3 units cubed. All right, so I'm assuming at this point that you guys can evaluate. Plug in 2, plug in -2, and subtract. That's what I get. All right, now part B says, let's change this function. Let's change this function here, this A function, even though I'm going to basically be doing the same thing. Let's make it bigger. Oh, that's too big. Please let me. All right, good. Okay, so I'm going to be basically doing the same thing that I did before, but now instead of a delete, instead of a square, I am going to use as my my perpendicular a equilateral triangle. I'm trying to make an equilateral triangle. And again, this equilateral triangle, as it gets closer to -2, is going to get smaller. It's going to get biggest at the y-axis, and then it's going to shrink it down. And that same picture is going to apply. So in an equilateral triangle, remember that the area of a triangle is 1/2 base times the height. Okay, well, we know what the base is. The base is this value. It's this distance here. So I can go, my area is going to be 1/2, and then it's going to be 2 square root of 4 minus x squared. Now I need to figure out what the height of each of these things are. Okay, well, that's not too bad, because I know something about equilateral triangles. I have a right angle here, I have a 60-degree angle right here, and a 30-degree angle here, so I'm trying to find the right triangle. So if this is x, this would be 1/2 x, and this would be x times square root of 3 over 2, just the unit circle stuff. Okay, so since I already know what the base is, that would be this whole distance right here. Half of that would be just square root of 4 minus 2, and then multiply by square root of 3. So I'll get, this thing would be, so this height now is going to be square root of 3 times square root of 4 minus x squared. And so these twos cancel, and then the square root of 4 minus x squared times square root of 4 minus x squared gives me square root of 3 times, now just 4 minus x squared. That is now my a of x formula for this particular shape. All right, that's just me using the area equation. So I'm just going to plug it in again. It just becomes, once again, it goes from -2 to +2. My new area equation, square root of 3 times 4 minus x squared dx. And nobody likes dealing with square roots, but luckily it's a constant, so I can just move that out. So square root of 3 there, -2 to 2, and then 4 minus x squared dx, and hey, look at this. We can do simple power rule integral on that thing. So I got square root of 3, and then it's just going to be, well, it'll be 4 over 2, or no, just be 4x, and then it will be 1/3 x to the third, And then that thing is going to be evaluated from -2 to +2. And once again, you just plug and chug here. And I'll leave that for you just because we're getting to be quite long. You can press pause and calculate it yourself. But once you evaluate that, it comes out to be 32 square root of 3 over 3 units cubed. And that's it. Okay, we are done. I know that's long, but here's Star Wars fun fact of the day. You've been waiting for it. The Corellian Engineering Corporation is a Star Wars spaceship manufacturing company that is based on Corellia, which is a planet that is inhabited by humans. And Han Solo is from Corellia, just like Luke Skywalker was from Tatooine and Princess Leia was from Alderaan. And the Corellian Engineering Corporation makes a lot of small and light freighters, mainly, not mainly, but one example is the YT 1300, which is the Millennium Falcon. It's not the only YT 1300, but the Millennium Falcon is a famous one. It also makes another light freighter called the VX 100. It's an older ship, and this one is the Ghost from the Rebel ship, or from the Rebel show. And so there is your fun fact, Corellian Engineering Corporation. There's a lot of other ones that are mentioned in non-canon episodes. Well, that's all I got there, folks. You have a great day. I'll see you in class. Bye.